All right, and we're back again. All right, this video is about pressure at depth, but let's first take a little look at air pressure, and something you probably don't think about all that much. But let's here we go. Here's good old Mother Earth underneath us, and here we go. Here you are standing there, and we'll give you a nice big smiley face. Something you don't think about is the fact that you are under a pressure. You see, in the last video we said that pressure is transmitted equally throughout a fluid. Well, that means that you're standing in a fluid right now. Now, we don't really think about the fact that you're standing in a fluid, but you are. Because, have you thought about what are you surrounded by? You're not surrounded by water, but you are surrounded by air. And you're underneath all this air. Now, this is the thing most people don't think about. Well, this air is exerting a force. This air is exerting a force. It's exerting a force against you. So right now, the very air that you are surrounded by is exerting a force on you. And therefore, it is also exerting it's also exerting a pressure on you. So the pressure due to this air, and this is in general terms because reality of it is it could change. Air pressure can change. Just for instance, it should be common sense as you're thinking about this, if you're on flat ground or if you're up on a mountaintop. Your pressure ought to be less on top of the mountain. Why should there be less pressure on top of the mountain? Well, this picture explains it all. You've got less air on top of you, therefore you are feeling less pressure for that reason. So there is the general idea of what's going on in this question. Most people don't think about this idea that pressure is being exerted on them, but pressure is. And in physics, we'll call that pressure 101,325 PAs. And you could use 1.01 times 10 to the 5 if you want to. I just go ahead and, for some reason, I've got the whole thing memorized, 101,325, so I write it down. Most people don't think about it, but your body, that means, let's take a look at the old human body a little bit closer. So here is that person's head. Here's what you don't think about that often. If air is exerting a pressure against your head, in theory, what has your head got to be doing? Well, that means your head has got to be exerting a pressure back out. If your head did not exert a pressure back out against it, what would happen to your head? Well, the air pressure would implode your head. Well, my head is currently not imploding. So that means there's a pressure inside my body. And you already know that there's a pressure inside your body. And that pressure has to balance out. The pressure in has to balance this outer pressure. Which is why if you've ever went up and on the hill or down the hill, you noticed your ears popping, balancing out the pressure, the internal pressure to this other pressure. And it's also why a lot of times you'll hear of people going scuba diving and going under the water, and that increase in pressure will actually cause their ears to implode at that reason. Now you've kind of got this. So we know we're under a pressure. Well, let's go to that very thing. Let's talk about scuba diving at this point. Let's actually go underneath the water. Sorry, I'm starting to think about Little Mermaid. Under the sea. Under the sea. I don't know any other words to that song. I'm sorry to let you down, but you're probably not watching this video for my singing. Although it's not bad. Here we go. So let's draw some water. Now, most people don't think about this. But let's think about the pressure underneath water. So now let's take this same person and let's draw them. Here we go. Now we're underneath the water here. So here they are. I went under the water. Apparently this person's got a tail or something. I don't know what's going on. But anyway, so we've drawn this person. They're underneath the water at this point. Here's the thing. What about if a person was standing on top of the water? If you were standing on top of the water. Well, you got to remember, air is exerting a pressure down. And that pressure due to that air, 101,325 PAs. There's that pressure due to air. Well, now you got to think, if air exerts a pressure due to the weight of the air, well, now think about being underwater, and this is nothing new. Most people are kind of familiar with this idea. If you're under the water, let's think about something. this water is going to exert a pressure on you. And also, you got to think this air is exerting a pressure on you. So when you are under the water like this, you are actually, the pressure in this problem, so I'm going to put big P right on that person's head. The pressure that is upon you is equal to PO. It's equal to this air pressure up above you, but it is also equal to the weight of the water above you. Well, we could do a little bit of general stuff, but pretty much deriving this is just rho G, and some books use different things, but I like using rho GH. So my rho's kind of ugly, but anyway, that's the density of the fluid that you're under. G, of course, is 9.8, and H is referring to nothing but the depth of the water in that equation. So how deep is that water, or how deep is that object under the water? Y'all, this is the generic equation to find pressure at depth is all this one is. So this is not all that bad of a problem. Matter of fact, if I can dig through my mess of stuff, we might actually try and work on these questions. Here's one actually given in the textbook that we have, and it just says, calculate the absolute pressure. And by the way, the word absolute pressure does have bearing in this problem. When you see the word absolute pressure like that, it's referring to, hey, this is just a P. And if you're wondering, why is that such a big deal? Well, keep working these problems and you'll find out later on in the problems. So calculate the absolute pressure at an ocean depth of 1,000 meters. So in this problem, here we go. Here, let's draw our ocean out here. Somebody in this problem or something is 1,000 meters under the surface of the water. Well, all you got to think, what is the pressure at this point? Well, the pressure at this point would be equal to the air pressure up here, which is 101,325, plus it would also be equal to the pressure created by this water. And now the pressure of this water is just that rho GH equation. So all we're going to do is plus rho GH. So there is this pressure down underneath here. So if I want to solve this problem, it told me everything I needed. Now it tells me that PO is 1.01 times 10 to the 5, but hey, you know, whatever. Let's go ahead and be nitpicky. Let's throw the real deal in. So let's do this problem. PO is 101,325 plus rho, and it says that the density of water in this question, the density of water is 1 times 10 to the third. So that's 1,000 times 9.8 times 1,000. 1,000 meters deep. So there's our pressure in this problem. And so if we want to try and get in a solution here, let's see if we can do this. 101,325 plus, and then we've got 1,000 times 9.8 times 1,000 is equal to, oh my goodness, what a pressure that we've got here in this problem. 10.9 times 10 to the 5, 10.9 times 10, I think it's 10 to the 6. 10 to the 6 PAs. Woo! What a tremendous amount of pressure. Matter of fact, so much pressure, I want to look at nope, I was wrong. Can you see my calculator? Stupid TI got an extra 1 in there. Let's repunch this. 101,325 plus 1,000 times 9.8 times 1,000. Try it again. What have we got this time? Looks like I've got about the same answer. I've got 9.9 times 10. Didn't change it by much. 9.9 times 10 to the 6 PA, which is an incredible amount of pressure. So that is a lot of pressure. Now, I want to bring up one other point. Some of these problems are going to bring up a subject known as gauge pressure. So problems are going to use this word, gauge pressure. Not gauger, but just gauge pressure. And by gauge pressure, I want you to think about, like, let's think we have a water pipe here. And so here's a water pipe. I'm going to put me a little outlet here. You see what happens with that water pipe, and I'm going to probably round these numbers off. You've got this water that's been pressurized inside the pipe. And now here this water is wanting to escape the pipe. This is at least my way of kind of thinking about this. So here's this water wanting to escape. Well, here's the thing you got to kind of think about. This water may be trying to get out, but you got to remember something. There is air all the way around this opening. That air is pushing back with a pressure of 101,325. I've just got a great question. What happens if the pressure in the water line isn't 101,325? Well, the air would push the water back out of the lines. You actually create, anytime the pressure in something is less than 101,325, say, for example, what if you had a container? What if you had a container? Let's just do a closed container here. Well, not completely closed. It had an opening. What would happen if the pressure in here, what would happen if the pressure, we'll call it P1, and this is your PO out here. What would happen if P1, that's the letter R, what am I doing? What would you do if P1, what would happen if P1 was less than PO? Well, if PO is the greater pressure, then you would actually create a vacuum and you would push air in until P1 became equal to PO. It would be a vacuum. I know I'm getting off subject, but have you ever thought in your life what makes a straw work? I know you probably don't think about this, but what makes a straw work? If you stick a straw in your favorite beverage, there's my straw. What makes the straw work? You got to think about something. You put your mouth on this part, blah, blah. Middle nose. Wow, this guy has, this is a terrible looking drawing here. But anyway, give him some big old ears on there. Anyway, what happens when you try and suck on the straw? Have you thought about this? Well, here's the thing. You're creating a pressure in your mouth. Let's put a P up here. The pressure in your mouth is less than air pressure. So what happens? You're not actually sucking the water into your mouth with the straw. What you're actually doing is you're creating a low pressure, and then the air pressure is actually pushing the water up into the straw. Holy cow, did that just blow your mind? Well, if you found that entertaining, by golly, today is the day that you get entertained. I'm actually going to do something rare. I'm going to show my face on this video. Now, it'll probably take me 20 minutes, too, to get everything set back right. Oh, no, I forgot I've got a beard. It's a pretty awesome one, actually. Normally this would work, but I have a beard, and it's not going to. So, oh well. Nope, not going to work. Why won't it work? Well, I can't get a seal. Have you ever stuck a cup around your mouth before and like sucked it? Sorry, I'm looking at my screen. Hello. But anyway, have you ever, that beard is huge. Have you ever stuck a cup to your mouth and just sucked and let it stick to your cup? Why does the cup stay on your mouth? Think about it. It's not you sucking the cup to your mouth. You're creating a low pressure inside the cup. When you actually suck on the cup, it's air. The air in the room that I'm surrounded with, the air is pushing the cup back against my mouth at that point. And in theory, if you suck hard enough, what happens to the cup? It crushes. It's not you crushing the cup. It's air pressure in the room crushing the cup. So let's go back down here and take a look at this problem then. So I explain, you're thinking, man, you just went around the world, and I just want you to do one more thing. Well, I went around the world for a reason. This word, gauge pressure, what happens is this. If you want water to come out of this pipe, the pressure inside this pipe, let's say that pressure in here, let's make it 105,325 PAs. The pressure in here has to be greater than the pressure out here. A lot of problems use the word gauge pressure because what happens is this. The gauge pressure is the difference. What is the difference between? So the actual pressure, in other words, the actual pressure you find at this spot, the actual pressure at this location is the difference between those two pressures. So gauge pressure is nothing but P minus PO. So if you work a problem and it says gauge pressure, it's just implying this P minus PO. That's all it's saying. Gauge pressure is P minus PO. And sometimes you'll work a problem that's like that. And sometimes you'll literally end up just doing this. You'll end up going into the problem being like P minus PO, and you'll just say, well, that equals rho GH now. Just like that. So if it says solve for gauge pressure, you're not solving for P. You're not solving for PO. Your answer would literally be like P minus PO equals 5,240 PA, something like that. That would be your answer if you were solving for a gauge pressure. So anyway, we kind of get that across. Now I'm going to go ahead and tell you the most common pressure at depth question. And this minute, 16 minutes long, and I don't want to go any longer, so I'm going to shorten it down. Plus, my bell is ringing, so somebody will probably be in here disturbing me in like 10 seconds. But anyway, let's do this. Here's that water. We know that there's air pressure. There's a PO of 101,325 up above the water. And now let's go down underneath the water, and let's draw us a submarine. I love that movie, Hunt for Red October. That's random as well, but ain't that a cool movie? I had a video game as a kid, and you cannot beat it on an old... Wow, I probably don't need to get a job drawing submarines for a living. Oh, yeah, they usually have like a little towery thing in here. So anyway, but let's say that this submarine has a window. And inside that window, we've got a little person. There we go. And they got a little smiley face inside there. Everybody's always got smiley faces. Now, I don't know if you've ever noticed it, but submarines usually do not have windows in them. Well, there's a reason. We're about to find out. How deep is this submarine? Let's say that this submarine is 500 meters under the water. So what we have to figure out right off the bat is this. One, there is a pressure on this submarine. A matter of fact, that submarine will eventually get crushed. They call it crush depth. If that submarine goes too deep, its structure will actually just implode from the pressure inside there. So, anyway, let's see if we can't find that pressure down there. Well, let's see. The equation for that pressure at depth is equal to P equals PO plus rho, that's not a letter, rho GH. And now we can plug in 101,325 plus P, which would be 1,000 times 9.8 times 500. Now that would be an absolute pressure at that depth. Now I'm going to do something. I'm going to make this thing realistic. Most of the textbooks don't. Plus 1,000 times 9.8 times 500. That we've got 5 times 10 to the 6. Well, that was great. So 5 times 10 to the 6 PAs of pressure. Now here's the thing. Reality, most of the books don't do. There's not this much pressure. It's close to it, but the thing is, the inside of the sub is pressurized, which means if you want to do this problem really, really realistic, you ought to actually leave off that PO. You ought to actually leave that off of it, because the reality of it is there's already a 101,325 inside. The submarine is already pressurized inside there, pushing back out against it, because we couldn't survive in there if there wasn't air pressure in there. We would explode from the lack of pressure ourselves. But anyway, we're going to do it the way the textbooks do. Most of the textbooks, they just put like an absolute pressure, and they do that. Usually then, the book will go on and say something about the radius of the window is 35 centimeters. How much force is on the window? If you want to find the force on that window from this pressure, just go P equals F over A. And all we'd have to do is 5 times 10 to the 6 equals force over pi, because it's a round window. Radius is 35 centimeters, 0.35 square. And we would have our pressure in this question. So 5, where's my little exponent? 5 exponent 6 times pi times 0.35 square equals, whoa, check out this force, 1924225. That is a tremendous amount of force on that window, which is why you won't find a window in a submarine, not one that's made for going deep. But anyway, not a real like Navy submarine. But anyway, the reality of it is, you should have left that 101.325 off. The reality of a submarine question, you ought to actually set it up to look like this. This is the reality. And then you solve for P minus PO. And that's what you set equal to F over A. Now that is the way you should do that question. It just depends on the book and your teacher as to what's going to happen. But I actually prefer this, because this way you're accounting for the fact that the interior of the submarine is pressurized already. Anyway, I am done, and I am out of here. Me and this fantastic beard say goodbye.